Hi there, welcome back to the channel. Welcome to another under-shelf module project. This is what I've been wanting to do for some time. It's to perform a function that I do all the time, and it's a bit cumbersome and a bit boring, and I wanted to automate it. And there's no better way to do that, in my opinion, than to create another one of these modules. You see it's getting quite long. The one I'm talking about is that one there. You can't see it, but you'll have to watch the video to figure out the details. Anyway, this video is quite long, so because I go into the design concept, the thought that went into it, the reasons I've made certain choices, and then finally I do the build and testing and show you the result. There's also a PCB that I designed, and PCBWay kindly sponsored the video and those PCBs. So if you want to build your own, I'm going to put those PCBs into the share section of the PCBWay website, and I'll put the link to that below. It's up to you. Now, this video has various stages, and the one that people sometimes want to avoid is all the schematic stuff. So in the video, at that point, I'm going to put a link or put an indication of where in the timeline you can go to if you want to miss all that stuff. Anyway, I do hope you stick around. This one is a follow-up to probably the most popular video series on my channel, which is the capacitance leakage tester. So this is sort of in the same vein, the same line, and I do hope you enjoy that sort of thing. And if you do, enjoy the video. If you've been watching my channel for a while, you will have seen this capacitance leakage tester that I designed and built into this module that fits under the shelf with all the others. This allows me to test the leakage across a film capacitor at a voltage that I can select. Now, for example, this is a 250 volt cap, so I can just up the voltage. I've got it in the off position. I can put it on the highest rating. This is up to 100 milliamps, which is just the safety measure. And I can go up to the 250 mark, for example. And I can see a little bit of leakage there, so I can just make it more sensitive. It's leaking. It's on the 10 milliamp range. So it's leaking about 2 milliamps. Now, this is incredibly leaky. This is completely useless. Turn it off, it discharges, put this down, and I've got my leakage on the capacitor. Now, this is incredibly useful for these old capacitors because although most of the time I just replace them with modern ones, sometimes you just want to see what the actual leakage is. And this is very convenient because it just sits here on the shelf and I don't have to pull it out from anywhere. Just switch it on and off I go. I also use this LCR meter, the DE5000, very useful. Allows me to measure capacitance. In this case, it's supposed to be 100 nanofarads. It's measuring 203. And if I've got an electrolytic, I can measure ESR and all that sort of thing on here. That's all well and good. But there is one other thing you've probably seen, which forms the basis for the main topic of this video. Let me show you what I'm talking about. You may also have seen someone doing this to a capacitor, putting an oscilloscope across it and touching it. And what you're getting is the induced hum, AC hum, mains hum. In my case, it's 50 hertz. In your case, it might be 60. That's going from my fingers through the into the capacitor and getting picked up by the scope. As you can see there, we're getting about 22 millivolts peak to peak. It's 50 hertz. Now, if I flip it around, I get a lot less. What does that mean? It means that the probe at the moment, you see when I touch it, it's picking up hum, right? It means that the probe at the moment is actually inside the outer foil, which is connected to ground at the moment, right? You see this capacitor is made up of like two sheets of foil with an insulator between them and is rolled up. Now, inevitably, when you get to the end, one of those sheets is going to be on the outside. That outside is called the outer foil. And when you've got the outer foil connected to ground and you connect your probe to what is effectively the inner foil, it picks up a lot less hum. Now that's significant. Look at that difference. Let me flip it around. See that? This side here is very obviously the outer foil, and you can tell that because these capacitors had this little marking on there. We can do it with another one, this one here. And again, we've got, whoa, this one is big. This is a huge difference. You can tell quite easily that that side is really picking up a lot more, which means that that side is the outer foil. And again, we can tell because they've put a mark on there. Now, with modern capacitors, we don't have that mark. And in fact, with modern capacitors, it can be either way. You can have the writing in the same orientation from one capacitor to the other from the same lot, and these will be reversed. Now, the whole idea is that you try and follow the rules as regards which side you put the outer foil on, because it'll reduce noise pickup. Is it important? Well, I'm on the fence about that, because with modern capacitors, you've got very little bulk. They're much smaller, so there's less pickup area for it to affect the circuit, but I still do it anyway. I go across the scope, I just put it across the scope one way, flick it around, do it the other way, and I can tell which side is which. And this task, it's not difficult, but it's annoyed me for some time, and it's annoyed quite a few other people. And quite a few people have tried to make automatic detectors for this, so you don't have to go through all this rigmarole of putting up scopes and everything else. And I figured I'd do the same, and especially as I decided that the perfect place for it to be would be alongside the capacitance leakage tester, which means that this guy's going to get moved along, and I'm going to build this into one of these modules and put it right next to the leakage tester. And this will make my capacitance testing, both leakage and outer foil testing, almost automatic on my workbench, available all the time, and very, very simple to do. So simple that the question of whether it's important or not doesn't even come into my brain. I just do it. And I'll do it really on the spot as I need it, because sometimes I'd get a series or a stock of capacitors and go through all of them and mark them and all that. In this case, I don't even have to do that. I can just do it like this. And I wanted to do this in the same style, in the same module shape as I have for the other modules on the bench. And that's what I'm going to be doing today. As you can probably guess, I got PCBWay to produce some boards for me. They're sponsoring this video, and I thank them for it. Thank you for the boards as well. And these came out exactly the way I planned. And what I planned was to build up this board with the schematic that I'll show you momentarily. And this would fit in the back of one of these modules like this. I'll have all the controls and indicators on here. And that will then just fit nicely into my undershelf system. And I'm going to build up this board, and it's not complicated. It's just a mishmash of little bits and pieces that, like all schematics these days, you've got tried and tested systems that you just use as you require them. And the boards actually came out very, very nicely. I decided to go for black this time. I haven't had a black one for a while. This board has got components on both sides. This would be the side facing the back with most of the components on here. And then everything that has to do with the front panel comes out here. And as you can see, there are LEDs, LED, a switch, a pot, and the two input terminals, but I'll explain that in a minute. The basic idea for this video came from the fact that we have a signal. When we look at the scope and we touch it, we have a signal that is, in my case, 50 Hertz. And I think it was about 20 millivolts peak to peak. That is not a big signal, but it's also not the smallest signals that I've ever seen. So we can do something with that. Once we've got a signal, which is effectively a 50 Hertz audio signal, we can do stuff with it. And what do we want to do with it? We want to manipulate it. We want to then be able to detect it and be able to measure it to get the relative amplitude between the one condition, which is when you've got the leads in one way, and then the other condition, which is when you've got the leads in the other way. So the first thing to do is to try and amplify, buffer the signal, and that's pretty simply done. Let's take this as the input. I put a resistor across it, give it an earth reference, a ground reference. This should be quite big, so I chose 2 meg 2. And so when I say in, that's where our capacitor under test is. Okay, so you're touching there, you're inducing this sine wave over here, and you're now going forward. Now, what are we going to do next? Well, we need to probably buffer it first. So I'll take one part of an op amp, just a non-inverting buffer. And so that means we've got the same signal that we had here. We've got it here. Okay? Then what do we need to do? Well, we probably need to amplify it, probably quite a bit. So I'm going to put a non-inverting, remember we've got an op amp here, so we can use more op amps. Put in a non-inverting op amp circuit, which would have a resistor to ground, and it would have a resistor to the output. Okay, that's our normal non-inverting op amp amplification stage. And the way to do this is to try and get quite a bit of amplification. Now, I tried various things here. I tried various multiplication factors here, and I decided to go for a 1K over here, and I tried a 22, 25K pot, I think it was. It wasn't enough. So in this case, because I want to make it adjustable, so I can adjust the sensitivity depending on which capacitor, what type of capacitor I have. Some of them, as you saw on the demo on the scope there, some of them really produce a huge signal. Others produce smaller signals. The bigger the capacitor, the smaller the signal is going to be. So I'm going to make this a potentiometer, and I ended up working with 250K. So we can multiply. I mean, if this is down at 0, okay, the gain stage of this is 1 plus RF over R1. So if we've got RF at 0, the amplification is 1. Or if it's at maximum at 250K, divided by 1K is 250 plus 1, so there it's 251 times. Okay, so we've got quite a bit of leeway here. You can change the pot depending on how much gain you need. This might be too much, but I decided to leave it like that. So what do we have here now is a signal, that signal, which has not been inverted, but it's been amplified. Quite a bit. Now what do we do? Well, this is where I wanted to go into a comparator circuit, but to do a comparator circuit, I wanted to be able to light up various LEDs depending on the level of that signal, the amplitude of that signal. So the first thing I needed to do is convert this into a DC voltage representative of the amplitude. So it's basically a peak detector. And a peak detector we can do quite simply with another op amp. This is really going crazy with op amps. And this one is also non-inverting. And that goes back there. Now, what you would normally do is you would normally just put this through a diode over here. You could put a diode over here and it would half-wave rectify, but you'd lose the 0.7 volts of the diode. But there's a trick that you can use, which is actually quite simple, that you can use to half-wave rectify a signal without losing that 0.5 volts. And this is it. You put your diode in here, and I used a 1N4148. No big deal, doesn't have to be anything special. That'll do the job. This thing's going to be pulsing like crazy, okay? This is going to be like that. A normal half-wave rectified signal, but you want to make that DC. So the best way to do that is put a capacitor here. And that means, and I believe I tried various values and I came up with 1 microfarad. That means that whatever happens here, this amplified signal then gets rectified, half-wave rectified. Because you've got that capacitor, it'll do something like this. You've got effectively a DC value, DC volts over there, depending on the amplitude of that. The amplitude of that depends on the gain you put on there. The gain you put on there depends on how small that signal is. But if you test the capacitor here and adjust this to get you to the level that you want, and we'll talk about that level in a second, then you can just adjust the gain till you've got the level that you want, not touch the gain again, and then you can flip this around and you can get a relative amplitude. So what we have over here is a DC voltage proportional to the amplitude of the signal that our capacitor is picking up. Now what do we do with this? This is where we go into a comparator circuit. Now you can buy ready-made comparator ICs, but what I realized is I was already using op amps. There's already 3 on here. And op amps are quite cheap, especially the ones I use. The TL072s are very cheap. There are 4 op amps in one package, and I like them. I've got a lot of them. So I decided to do that. I decided to use a comparator circuit with op amps because I realized I don't need a lot of indicators. I decided on 4 indicators. That gives us 1 op amp for the indicators, and those indicators are going to tell us what relative level our signal coming in is compared to a reference level that we set up. And the reference level we set up, first of all, let's just draw the comparators here. And our comparators are going to drive LEDs. So if we want to drive an LED, we just put a resistor and we take this to ground or to the negative voltage. So let's do that to all of them. Now, this is where things get a bit interesting. We want this LED to go high when it's above a certain threshold. If it's beyond that threshold and it hits a second threshold, we want this one to go high. If it goes through a third level, we want that one to go high. and so on and so forth. So it gives us an indication of the level of the signal. Now, the way to do this, a comparator with an op-amp, is very simple. If we take, for example, that input signal that we talked about, that DC voltage that represents the amplitude of our audio signal, our 50 hertz signal, then all we need to do is create 1, 2, 3, 4 different steps that are going to give us reference values. And we can do that with resistors, and I'm going to do that relative to ground. So we've got one resistor here, another resistor. Now let's say I set that for, let's call it 0.2 volts, and that one for 0.4 volts, that one 0.6 volts, that one 0.8 volts. How am I going to get that to work? Well, I need to use equal resistors because I want this to be linear. So I used 1K resistor, 1K resistors, and then I decided to put a trim pot at the top here, supply that with V+. So I can adjust that, and this one was a 22K pot. It allows me to, depending on how I set that pot, I can set this to 0.8 volts over here, and if I've got 0.8 volts over here, then I'm going to have 0.6, 0.4, 0.20 at ground, right? Because I want this to go high when the input level is higher than that threshold, higher than 0.2, what I need to do is make sure this goes into the negative, the inverting input of the op-amp, and it goes to all the inverting inputs of the op-amp. And then the positive is where I'm going to feed that input signal. So these positive, the non-inverting inputs, are actually going to be tied together and DC volts in. That's where our input signal comes in, the one that we've rectified and smoothed out and filtered out over there. That comes in there and it feeds it to the inverting input. Now what happens here is, if that signal's 0.1 volts, that 0.1 volts there is lower than 0.2, so that's off. And it's lower than 0.4, so that's off. That's off, that's off. Now imagine if it's 0.5. If that voltage there is 0.5 volts, then this here is 0.5. Now the op-amp will just switch to the positive rail. It'll make that high. So that'll be the positive voltage plus V going through to ground or to negative voltage. We'll talk about that in a second. And that'll light that LED up. Now we've got 0.5. If that's also 0.5, that one there is 0.4, so that one will also light up. That's 0.5, that's 0.6, that one will not light up. That's 0.5, that's 0.8, that one will not light up. So you see we've got two LEDs indicating that our DC voltage is sort of halfway through, right, across these level settings. Now what I decided to do here is, normally you take this to ground, the LEDs, but I wanted a bigger span. You'll see why in a minute. So I decided to take this to minus VCC because we do need, I do create, call it minus VCC. I do create a split rail system, but that's basically all it is. And what we're going to have here is we're going to have plus V, we're going to have minus V. Across plus V to minus V is going to be 9 volts. So this will be 9 volts relative to that. So 9 volts divided minus 2 volts approximately voltage drop across the diode. We've got 7 volts. And I want a few milliamps. These are ultra bright LEDs, so I decided to put in 2K2s on here. 2.2Ks, it gives it about 3.5 milliamps per LED, and these LEDs are very, very bright at that type of current. Perfectly good for the purposes that we have here. And we've got just a few more things to do. So that's the comparator circuit sorted out. Let's look at the next stage. Now, the first thing that I decided to do was to use a battery on here. I wanted to use a 9-volt battery. And with a 9-volt battery, with op-amps, you need to create a split rail. So you can do that very easily. And remember, I have used 3 op-amps on here. And the TLO-Sim4 has got 4 in one package. So I can simply do the usual thing, which is I've got plus 9 coming in. There's 0 volts. I can put it across 2 resistors. Equal resistors. I'm going to make them about 10K each. We don't want too much current lost. You can make them higher, but we just then use one of those op-amps like that, and that becomes our ground. Right? If you haven't seen that done, It's all over the place. It's very easy to do. And that's also non-inverting. Sorry, wrong way around. Non-inverting. So that gives us 4.5. That's 9. That'll be 4.5. So that's 4.5, which means that if we look at V plus equals 4.5 and V minus equals minus 4.5, all of this relative to ground. That's important to remember, okay? So the 0 volts is not ground in our case. The other thing that I normally do is I put in a small capacitor here just to stabilize that, keep that reference nice and stable. And what I used was, I'm just checking here, I think I used 47 microfarads. You can use 10 microfarads, no problem at all there. And the other thing that I like to do is, there's our plus V. I put 2 capacitors from ground to plus V, ground to minus V, very near the supply lines of the op amps. That's 0.1 microfarad ceramic. That's all it is there right now. The relay. The relay is a strange one. I had the relay. I wanted to use the relay. I did everything I could to use the relay. And all I want the relay to do is to flip my polarity of the leads of the cap as I push a button, or I could put a timer on there. I decided to push a button, use a button, and let me just draw this, see if I can explain this. We've got our coil here. I connected that to ground. This is a 5 volt, I think it's a 5 volt, or is it 9 volt relay? And what I want to do is, when I push a button here, I put plus V there, I push a button on there, it's going to switch the coil on and alternate the relay. Now this relay is double pole, double throw. Okay, so what we've got here is, we want, there's our one pole, let's just draw them. That's one pole, that's the other pole. And what I want to do is I want to take the capacitor that has 2 contacts, right? And I want to be able to flip these around to ground. We've got 2 outputs. One is going to go to the input of our circuit, that one there. One's going to go to there, and the other one's going to go to ground, right? So this one is going to go to ground. Now, we've got to make it so that these things flip around, and it's very easy to do, because if you've got this in the normally off, or normally the normal condition, in other words not activated, you can make it go like this, and this one goes to there. So in this case, we've got that side connected to ground, that side connected to our signal. Now what happens when this thing flips around? When this thing is activated, that goes on like that. And then what you do is you make this. So this one was going to there. Now it's going to go to the other one. So it's going to go like that. And then that one there is going to go to there. Does that work? When I flipped it, I've got this guy going to ground and that guy going to input. Yes. So look at the red. The black is that one, that top part there goes through there, to the input. That one goes through there, through the black connection to ground. When I flip it, when I activate it, then that one there goes to there. It comes through here to ground, and that one goes up there to the input. Perfect. It works perfectly well. Now, the other thing I want to do is I want it to tell me when I alternate between these 2 states. I want to be able to put an LED. I want to put an LED that's going to shine there and there. It's going to go on at the inputs to tell me which one is connected to ground at that time. And the best way to do that is simply to have that working from your push button switch over here. And you can put 2 back-to-back LEDs on here. These then go to, and they go to minus V, or V minus. Now what happens here? Well, remember, V minus relative to ground is 4.5 volts, all right? And when we have this thing open, when we don't have this depressed, there's no voltage there, but there is a voltage there, 0 volts. That's 0 volts. So this coil is simply a resistor. And the voltage then between there and the lead, or rather the current flows from there through the lead, because this is a higher voltage than that one, goes through there. This thing will have 4.5 volts across this circuit. And so you've got 4.5 volts, very little voltage drop across that coil, meets the diode. The diode drops about 2 volts, and we've got this, and I believe I used 2.2K as well, just to limit the current. So we're using the fact that our coil is basically a very low resistance, low DC resistance path to ground through that to give us a light on when, which condition is it? When this is ground, okay? Now, when you push that button, suddenly that becomes 4.5 volts relative to ground. That is minus 4.5 volts, so suddenly we've got 9 volts across that. It's going to pass more current, but the actual brightness between the two is not that significant, as you'll see. And now this one will light up and that one won't. There's no problem with them being back to back. In fact, one protects the other from an excessive voltage across it in reverse. So that's the way it works. And I'll show you the full schematic in a rather more reader-friendly format. Let's go to the screen. Let's start with the power supply. Remember, we are using 2 quad op amps. This is the first one. It's labeled 2, don't worry about it. And we're using the second op amp just to do the comparators and drive the LEDs. So let's look at this one first. We have the 9-volt battery coming in. The reason I want a battery is I want this to be completely self-contained and sit at the back there. I'll put the battery inside. It doesn't draw much current. I don't use it for long extended periods of time. I will have a switch on there as well, as you'll see. So we switch it on when we need it. We switch it off when we don't. And there's a reason why there's no switch indicated here and why there's no power on LED indicated here. It's because when I switch it on, one of these will always come on. So we will have an LED on the face telling us the unit's on. So I didn't bother putting another one in. Now, here it is. This is that 1 resistor, 2 resistors, voltage divider, divides it neatly in 2, 4.5 each way, with a capacitor to stabilize the middle. 10K, 10K, that means 20K across 9 volts is about 0.4 milliamps, something like that, 0.45 milliamps. And what I've done is I've put in the option for a little pot, a 22K trim pot, which you use instead of these resistors. And the reason for this is that depending on which op amp you use, the output swing can sometimes go closer to the one rail than to the other. Usually I believe it goes closer to the negative rail than it does to the top rail. So if you don't want to make this 4.5, if you don't want to make it plus 4.5 minus 4.5, you can actually make it plus 5 minus 4. So you can adjust it depending on how you want that. We may try that out and I'll show you the result when we do the testing. So there's our reference voltage. Let's call it halfway for now. So whatever comes in here comes out there. And that becomes our 0 volts. That becomes our ground. And we now call the 9-volt rail plus V or V plus, and then the 0-volt rail from the battery, we call it V minus. These here are just in order to get the spaces on the board to place these near the supply rails for the op amps. It's just decoupling. It's always a good idea to do that. They're 0.1 microfarad ceramics. There we go. If we look at the relay circuit, it's exactly the way I described it, except that I had this indicated as ground. I'm not putting it to ground. This negative of the relay coil goes to the V minus because this relay is indeed a 12-volt relay, and it works perfectly well with 9 volts, which is what happens when you push that button and you've got V plus on here. So remember, from V plus to V minus, there's 9 volts. It works perfectly well. And so that is V minus, and then the LEDs go to ground because we always want a difference between the two. And it then is a question of seeing which one lights up for which position of ground you're looking at. We'll see that when I show you the actual device in operation. And this is wired up exactly the way I described it in the circuit description. Now, if we go up here, we've got the input here, the signal coming from the relay, 2.2 meg to ground. These 2 diodes are in order to prevent spikes. If for some reason you get a very, very high voltage coming in, a spike coming in to the input, what will happen is that it will limit it to 0.7 volts or so, because it'll just pass that through to the supply rail. Depending on whether the spike is positive or negative, it'll either go to V minus or V plus. That protects our input here. And there's our unity gain buffer. So whatever comes in here is coming out there. There's our amplification stage with a 1K to ground and a 250K pot. So that allows us to extend the amplification all the way to 251, which is pretty neat. Here we've got our rectifier, which again is the signal's coming in, it gets rectified, but it's rectified relative to 0 volts. So we don't lose that 0.7 volts that we'd have across a voltage drop. It's fairly linear, it works pretty well. So what we'll have here is a half-wave rectified signal, but because of this capacitor, it smooths it out. And we need to put a resistor in here, which I hadn't mentioned, and that is so that if the signal drops, this voltage doesn't stay up there. It actually has a way of dissipating, lowering, in order to keep this voltage a true reflection of the amplitude coming in there. Otherwise, it would just stay up there, and because these inputs are very high impedance, it would take a hell of a long time for this voltage to actually drop. So that is used to discharge the capacitor. Here's our comparator, again from between V plus and ground. V plus will be plus 4.5 volts or so. I decided to work on about 2 volts. I think that's what I chose, or 1.6. So that there's about 1.6 volts. That is minus 0.4, minus 0.4. So it's 0.4, 0.8, 1.2, 1.6. The rest is dropped across that trim pot, and we can adjust it. Now that means that the highest voltage that we want coming out here is 1.6 volts to switch on that top light. That we can control by the gain of the spot over here. If we find that that the amplification is too low, if we find certain capacitors don't really, drive this enough, we can lower this. We can make this, instead of 0.4, 0.8, 1.2, 1.6, we can make this 0.1, 0.2, 0.3, 0.4. So we can make this very, very sensitive. But this trim pot is adjusted when you build it and then you leave it. The one that you do adjust constantly is this gain pot. And these, of course, drive these LEDs through 2.2K resistors, and they're going to V minus. So when this thing switches on, it'll go to the V plus or close to it, probably a couple of volts below that, but then it'll go all the way to V minus. So we've got, if this thing went rail to rail, we'd have 4.5 all the way to minus 4.5. That's a 9 volt drop across there, about 2 volts across there. So 7 volts divided by 2.2K is about 3.5 milliamps, which is more than enough for these LEDs, as you will see. And that is the schematic, drawn in a more user-friendly manner. And I designed the board based on this, of course. I made one mistake originally. I actually made this pot connected, pin 1 and 2 connected rather than 2 and 3, which meant that it actually got big as you go counterclockwise. I've changed that. I've corrected that on the PCB, and the new ones that I'm going to upload to the share section of PCBWay will be the corrected versions, so you don't have to do anything funny there. Here's our board, pretty simple, nothing too special about it. I try to keep everything neat. I try to make sure that, the wiring, the routing is uniform. I made sure that the spacing between components is as comfortable as possible. I've got 2 sizes here, for example. This resistor has, I think it's 10 millimeters pitch. And when I need to, I put a 7.5 millimeter pitch one. I've started changing that so that I can, more comfortably populate boards, but I also have the flexibility of fitting a small one when I really need space. So this is what we have, and I always find the 3D feature pretty cool. This is what the LEDs will look like on here. This is the lowest to highest. There's a pot will come through there. That's a switch. I'm not quite sure which one I'm going to use yet. I've got a few options, and I'll try this on the build itself. Well, that's it. That's enough screen time for now. Let's get to the project itself. Let me just show you the result. And as usual, so we don't have to sit here and watch someone solder again, I'm going to do the tap, tap, tap. And we've got it done. Magic. We've got these 2 inputs here. These are the terminals where the capacitor is going to connect to, like that, but obviously through banana jacks. And then I've got 2 LEDs. And what this is going to do is it's going to indicate for me which side is connected to ground. And what I do is I leave it as it is. These LEDs are going to light up like a bar graph and give me an indication of the size of that, or the magnitude of that picked up sine wave, which we saw on the scope. And what I'm trying to find is which side brings me a lower result. and I can change the sensitivity here as well. And I flip the grounds, I flip the polarity with this switch. I've had about 20 of these relays sitting in my bin for years. I bought them for some project, can't even remember what it was anymore, and I've never used them. This is one of those, what is it, Panasonic TQ2 relays. I'll put a link down below. And the idea here is to allow the flipping of the grounds, in other words, the flipping of the polarity over here by hitting this button, instead of moving the capacitor out and in. In other words, unplugging it, putting it back the other way, as you would do with a scope. You know, you would disconnect the one polarity one way and put it the other way. This thing does it automatically by hitting that or pushing that button. It flips the polarity, and the best way that I found to do that in a controlled fashion was to use a little relay. Very simple, they're very cheap, and you can use other relays as well, but I like the result. I could have had it sort of flip automatically. Mr. Carlson has one where he's got a 555 timer, and it flips. He uses quad solid state switches to flip the polarity, and then he looks at the scope and sees when was the signal lowest, and he can tell which side is the outer foil. I prefer to do it like this because I can control how long I want it to be on there, and it allows me time to adjust the sensitivity as well. And here's another iteration. I've been actually doing some tests on this with modern capacitors. If you don't know, old capacitors, bigger volume, and the outside shield is obviously more pronounced or more noticeable. With newer capacitors, it's not that bad, which is why they're probably better to use if you're not worried about the foil side issue. But we are working with modern capacitors, so I needed to make sure this thing was as sensitive as possible to the foil side issue. I put a 10 nanofarad capacitor here, and I did some testing, and I had to make a change. First of all, I changed the switch. I had a little micro switch which you had to push down, and I realized that to get this through to the faceplate of that of the enclosure was going to be difficult. So I put this one in. It's just a toggle, and it needed one more change, and that was to the trimmer over here. Now, this was the trimmer I had in here. It was a 22K trimmer. I've now got a 47K trimmer, and the reason is that I needed this thing to be more sensitive to very small changes. Now think about it. This LED here is going to trigger when it reaches one threshold. This is the next threshold, the next one, and so on. Now, if the differences between the foil side pickup of hum, and the non-foil side are large, you can have big gaps between these thresholds. However, if you're talking about a capacitor like this, which doesn't have a huge difference between one side and the other, in fact, in some cases I've had on the scope, I could hardly tell the difference. What you need to do is make sure that these differences, these gaps, are very small. So let's say that we had 0.4 volts, which is what I had, 0.4, 0.8, 1.2, 1.6. To achieve a big enough difference between one side and the other on a modern cap might not be enough to trigger a different LED, okay? And we obviously want as much difference as possible. So what I did is I went down and I adjusted this to 0.1, 0.2, 0.3, 0.4. So I adjusted this trim pot over here to 0.4 volts, and I can show you that. It's a little bit tricky to do it with this particular setup, but I know that my 0.4, the highest threshold voltage, is actually on pin 2 of the IC. So I'll probe pin 2, and this is where I adjust it. There we go, 0.4 volts, which means that my other thresholds, if I test them, I've got pin 2, 6, 9, and 13. 13 should be the lowest. Let's see if I can get this. 13.1, 9.2, 6.3, and 2 pin 4. What we have done is we've ensured that the difference between one and the other is 0.1 volts. And we can still play with the gain, okay? Now this is a situation, I've got this, I'm not touching this, but if I touch it, it obviously goes up. Let me leave it as, let me do that. What I've got here, trying to get this to video this is difficult. I've got 2.5 LEDs. Let me go to 1 and flick the switch. 2, 3. See that? I could probably still make it more sensitive, and I'm going to do that before I put it in. Actually, what I'm going to do, because I have to get to the back of the board, I've just shorted the power supply. I've got to get to the back of the board to adjust this. I'm going to put a hole in the back of the enclosure so I can go through the back and adjust it, because this thing's going to be difficult to adjust once it's in the actual enclosure. Let me just make sure everything is hunky-dory. Yep. As you can see, if I touch, this is an easy way to know which side is ground, actually, because presumably that is the ground. And if I touch it, it does very little. If I touch this one, look at that. If I flick it around, now I know that's the ground. So if I touch that side, very little happens. But if I touch that one, see that? So that tells me that's the pickup line. So that must be ground. So I've got these LEDs wired in correctly. If I do it the wrong way around, it'll give me reverse results. Now what I need to do is put this in the enclosure. Let me show you what I've done for the enclosure. This is it here. I designed the front faceplate on, what was it, Illustrator. Made sure that I got this as close to the physical layout of the board, of the components on the board as possible. And obviously I got those measurements from the actual PC board layout. And then I printed it out on a laser printer on self-stick, self-adhesive paper. I've actually found self-adhesive film before. I couldn't find it this time, but I did it on self-adhesive paper, and it's sort of a matte finish. And then what I did is I stuck it on here, exactly on the front here, cut out the holes, and then sprayed it with lacquer, just matte lacquer, just to protect it. It feels good. And then, of course, I cut out the pieces of the faceplate or the paper that are on the holes. So now what I need to do is just populate this, and I've got a switch for the power up here. It's the same type of switch as I've used here for the flick or the flip of the grounds. So it makes it all look uniform. I'm going to put this all into the enclosure, and then I'll be able to show you, test this properly, and not have to flick around with all this stuff. I'm just using a 9-volt battery, and I'm going to put it at the back here. Normally what I do is I just use a bit of double-sided tape or foam just to hold it in place. These things last a very long time. And if they don't, I can always just add a DC socket at the back here. I've actually got an idea to power the entire underside with one supply with various taps off there. So I might put one here later, which will bypass the battery. But for now, I'm going to use the battery. Next time you see this, it should be in there. And here she is, all done. This lacquer that I sprayed on here protects this from grease on your fingers and things like that. The sensitivity knob is a little bit big, but it's one that matches the others that I've used on that panel before, so I'm leaving it in. We've got the indication of the lights, so it's going up, and foil side is low. Well, you have to know what that means. When you put it on, one of the lights comes on immediately, depending on which side the ground is shorted to. And you'll notice that I've put a bit of heat shrink on here, because if you're holding the capacitor on here and you touch that metal, it changes the sensitivity. So you get these little plastic covers for these switches, for these toggle switches. So I can get one of those. I've just put in some heat shrink, same thing. And it's working quite well so far. Let's look on the inside. Inside, I've got everything facing the front. I don't have anything pushing this forward because the volume pot is sort of acting as the anchor. So it's good enough. This side is probably a little bit loose because the LEDs going into there do create a bit of friction, but probably not enough. If it proves to be a problem, what I'll do is I'll put a bit of foam at the back here just to push it forward. The battery's in here with a bit of double-sided tape on there. It's good enough. It's going to last a long time. I don't think I'm even going to need to put a DC supply here, but I can always do that. And now this thing's ready to go into the cabinet. But there's one more little innovation that I created, and that is I made side panels for these bracket units. This was 3D printed. As you probably know, I've become a great fan of DIY 3D printing, and now they've got side panels. So This thing just clips in. I don't need to really worry about screwing it in or anything like that. If I want to, actually that switch is pushing that one a little bit forward, so I'll have to just taper that off a bit. If I want to, I can always put a little blob of glue, just a dab of glue, just to hold it in place. And this thing's ready to go on under my shelf. And then I'll show you some real world testing, because there's one more innovation that I've created for the sockets here, for the banana plugs and sockets. All right, good, I'm happy. All right, folks, let's do a proper test on this thing. It is right next to the capacitance leakage tester, which is appropriate. And I take a modern capacitor. I can just flip it in there. If I want to put it in like that, well, let's switch it on first. Put it in there. And it doesn't hold. What are we going to do? Well, I made these things. I don't like unscrewing those on banana plugs to get to the back of them, so I just took 2 croc clips and I soldered them to banana plugs, and they fit in there like that. So it's very easy to use. And we go up till we get just 1, and we've got less than 1, but we need to touch it, right? There we go. 3 lights on, 2 lights on. So the lower side is that one, so that's the foil side. So I can then just do a little mark there. And what we've found is that the foil side is giving us a lower reading. See that? The difference is very small. We're getting a bit of the second light. We're getting the second light flash on. So the lowest is that one. That's the foil side. I've marked it. Now, some of these capacitors are easier to read than others. If you remember this one was a real gossip monger. She told us everything we needed to know. See that? Big difference. The lowest is that. It's that side. We know there is a band on there anyway. Let's try this little guy over here. Now, obviously, testing foil side of these alt caps is a waste of time, because you've got them indicated on here, and it seems that that is the foil side. Let's just check. Yes, it is. So 2, 3. So the lowest is that one. That indicates that light. That's the foil side. We know it is because it's got a band on there. Very convenient. Here's a big foil cap. The bigger the cap, the more difficult it is. See, it's very, very difficult to determine. Just get that light to flick. That's dead. That's just there. So that's the foil side. Yes, it is. So you see, depending on the quality of the cap, the age of the cap, it can be more or less difficult. But you can tell which side is foil side. You can check, as I said. See that? If I touch the side, I'm getting a signal. If I touch this side, I'm getting nothing. It means I'm touching ground, and that's telling us that is ground. So that is correct, okay? If I flick it the other way, see, I'm getting a signal there. I'm getting nothing there because that is ground, and that is telling us that that is ground, so that is correct. So, this is fantastic. I like this. I really do. I'm like a kid with a new toy. The capacitance leakage tester has got a brother, or sister, or whatever you want to call it. Let's not be sexist. By the way, this project got featured on Hackaday, and I don't know, somebody must have proposed it because I never did. So maybe someone will propose this one, and it'll feature there as well. Who knows? Anyway, I think it's a fitting addition to this row of under-shelf modules. I'm really happy with the result, and this thing is going to get a lot of use. I may even get brave and just do this. Because you see, if I do that, then all I need to do is put a cap across it. It doesn't do much, does it? No, it doesn't make much difference. So I can either fit them in the holes or I use those clips. I don't think these things are going to be very useful, so I'll just leave them out. And that's it for now. I do hope that you find this useful, and if you do, you can go ahead and build it yourself. You can actually get the PC boards made at PCBWay. I'm going to put the share link for the boards in the description below. Cap foil detector, over and out. Thanks for watching. Bye for now and stay safe.